Hey everybody. I am going to be doing my PowerPoint a little different this time. I'm going to be actually using my slideshow and talking to you from my desk. I'm going to be talking a little bit about orbital filling diagrams. So let me do my share screen here, and I will, oh, where is it? I don't know where it is. Hang on. There it is. Okay. All right. Let me go back to the share screen. Oh, there it is. Okay. So, um, now we had talked a little bit about electron configurations, and in doing so, talked about the 1s2, 2s2, and how you actually write an electron configuration. Now we're going to be expanding on that, and we're going to be showing you how to take those exponents and actually put those electrons in what we call an orbital filling diagram, because right now you have all the electrons kind of compact together. So now we're going to be representing these individual electrons with arrows. Okay, now some arrows are going to point up and some arrows will be pointing down, because electrons, as you know, are negatively charged. So they can't actually sit in the same orbital together. One's got to be spinning up and one's got to be spinning down, okay, because like charges repel one another. So when we do these orbital filling diagrams, the orbitals are going to be represented by boxes, okay? And they show the sublevels and orbitals that exist at each principal energy level. Now, a principal energy level is a row number on the periodic table. So when I refer to the term energy level, I'm referring to the actual row on the periodic table. And each box will represent one of the orbitals, and groups of boxes represent sublevels within the orbitals. Because as you know, as we're going through this, I had you guys color your periodic table in 4 sections. So the S sublevel has 2 columns, meaning there's going to be 1 orbital. The P sublevel has 6 columns, meaning you're going to have 3 orbitals. You always have 2 electrons per orbital. The D sublevel has 10 electrons, so it's going to have 5 orbitals, 2 per orbital. And then the F sublevel has 14, so it's going to have 7 orbitals, 2 per orbital, okay? Now, 2 principles and 1 rule determine how the electrons are filled in the principal energy levels and sublevels. So there's something called the off-ball principle. So electrons will fill orbitals starting with the lowest energy orbitals first, okay? So that means 1. Row 1 is always, it's going to be, I know it's at the top, but because the number is the smallest, it's at that's the lowest energy level. And so you work your way all the way up to 7 being the highest, okay? So then you have the Pauli exclusion principle saying a maximum of 2 electrons can occupy each orbital, and they must have opposite spins. So each time you have an orbital, okay, you can only have 2 electrons within that sublevel, okay? And they must be in 2 opposite directions. Remember, I just told you that like charges repel. So they can't sit both going this direction, okay? So electrons are traveling. They can't just both travel up in this direction. They've got to be opposite. So you've got to have one spinning here, and you've got to have one spinning here. So one arrow will go up, and one arrow will go down. So one points to the north, and the other points to the south. And then finally, you have Hund's rule. It says electrons are distributed into orbitals of identical energy or same sublevel in such a way as to give the maximum number of unpaired electrons. So what they're saying is, before you start drawing the arrows going down, you must fill the sublevel, okay, first with all of the arrows going in the up direction before you can start putting anything in the down direction. It's kind of like if you were going on a school trip and you blocked off a group of rooms, okay? Because they told you, oh, you're having 5 people on this trip, okay? So you go 5 people, then all of a sudden we have 8. Uh-oh, we have 3 people, but there's no more rooms available. So what are those people going to have to do? Well, they're going to have to start doubling up, right? So you got these 5 rooms, so you'll put 1 person per room, and then these extra 3 people, they're going to have to pair up with somebody. So you're going to have 3 other people paired up with in 3 rooms. Okay, so that's kind of what Hund's rule is saying. You're going to fill your unoccupied rooms first, and then if you have excess, you're going to go back and double those rooms up. Okay, so electrons are always filled in their ground state or their lowest energy state. So they're always going to fill row 1 first, then row 2, then row 3, then 4, 5, and so on. Okay, you have to fill the entire energy level before you can move on to the next energy level. Okay. All right, so in the hydrogen atom, only one of the sublevels within a principal energy level have all of the same energy. So each box represents an orbital. So as you can see, n equals 1. So that's row 1, and that's 1s. So these orbitals are representing each row. If you notice up here, you have n equals 2, meaning row 2. So the energy level row 2, you have a 2s and you have a 2p. Notice how in 2p they are broken up into 3 boxes. Remember, the p sublevel has 6 electrons. So you have 2 or 1 box per 2, right? So 3 boxes, 6 total electrons. And then if you go to row 3, you have 3s, 3p, and the 3d. D has 5 boxes because there's a total of 10 electrons. Okay? In multi-electron atoms, the sublevels within a principal energy level have different energies, okay? Sublevels within a principal energy level, so it splits. When you write the order, it's always SPDF, okay? So you have S first. So down here with my arrow where I'm pointing, you'll fill 1s first, then 2s, then you go 2p6, right? Then 3s, then 3p6. Now, as you can see, 4s, okay, numerically comes before 3d. So you're going to fill 4s, and then you're going to go to 3d, and then 4p, okay? Now, helium, okay, now notice these shapes that you see. So this is helium's orbital diagram. Now, S is represented with a sphere, okay? So when you're looking at the shape of S, it's actually a sphere. P is a figure 8. Now, notice how they're all looking in different directions here because you have X, Y, and Z, all right? So what that means is these are rotating in 3 different directions in the X, Y, and Z direction. And these clouds, these little teardrops here, you actually, an electron will be in each of the teardrops, okay? That's where the 2 electrons are filling in right there. So helium has an electron configuration of 1s2, okay? Meaning it has 2 electrons in its outermost shell. So you have, notice here how in the first energy level, I've got an arrow pointing up and an arrow pointing down, okay? That represents the 1s2 configuration. Remember, they cannot be in the same direction because electrons have like charges, meaning they're going to spin in opposite directions. So this would be an orbital diagram for helium. Okay, now lithium is 2s1, but remember, you have to, just like we talked about the electron configurations, you have to fill the row before you can jump to the second row. So here you're going to have 1s2 followed by 2s1, okay? Now we have boron. Boron goes to 2p1, okay? So right here you're going to fill up 1s2, 2s2, 2p1. And so that p1 is going to go in that very first sublevel, the orbital right there, okay? It's going to go right here. Now, you are not going to double this up with the next one, because remember, we talked about this. You're going to fill all of the up arrows first. You're going to fill all the single rooms first before you go and double the rooms, okay? So now the next one is carbon, which follows boron. So carbon's configuration is 1s2, 2s2, 2p2. So in this configuration, you're going to have your orbital filling diagram. So you're going to have 1s2, 2s2, and now 2p2. We just talked about that. You have to fill the up arrows first. So you're going to keep going until you can't fill any more boxes before you start doubling up, okay? Now, electrons occupy the lowest energy orbitals first, which we call the off-ball principle. No more than 2 electrons occupy each orbital. That's the Pauli exclusion principle. So you cannot have more than 2 electrons in a box, okay? Now, why do electrons in the p sublevel occupy separate orbitals? Okay, so it takes a little bit of energy to pair up electrons. So single electrons occupy different orbitals of the same energy first. So this is why you have to put them all going up before you can start doubling them up, okay? All right, so here's carbon's diagram, all right? So if you look here, oops, I didn't mean to do that, sorry. Okay, I'm gonna wait for that to go away because I want you to see the bottom part down here, all right? So as you can see, you have your orbital filling. This is the energy. Now, when you guys do this normal, I'm going to have it written like I do at the bottom here, where you have carbon, the C, and then you have these boxes, okay? You're not going to have all this spread out in this big diagram. The boxes are actually going to be right next to each other. So in this particular one, you've got 1s2, so up and down, 2s2, and 2p2, okay? That's for carbon. That's how you would write that configuration. All right, so here's an example of, 1 through 10, okay? So remember, we've already done this part, this configuration part. We've already done that. Now let's look at the boxes. So hydrogen has a configuration of 1s1. So you're going to have this box and you're going to have an up arrow, okay? Now helium is 1s2. So you have an up and a down arrow, okay? Lithium is 1s2, 2s1. So you have 2 electrons here and then 1 pointing up there. Beryllium is 1s2, 2s2. So beryllium is going to look like that, okay? Now, remember, when you, in the s orbital, since there's only one orbital, you'll go up and then up and then down, okay? But the p, remember, the p has 3 sublevels because you have a total of 6 electrons. So there's going to be 3 boxes here. So in boron, like we just talked about, you're going to fill up 1s2 and 2s2. And then when you get to the p, you have 3 sublevels within the p orbital, okay? And so you're going to go just fill that very first one. Then you go to carbon, 1s2, 2s2, 2p2. So you're going to have 2 electrons there, 2 electrons there, and then you're going to go 1, 2, both going up, okay? You don't want to do your down arrows until you've filled that sublevel with all up arrows. Now look at nitrogen, 1s2, 2s2, 2p3. So you're going to fill up your 2 s orbitals, and now you're going to go 1, 2, 3 there, right? With them, oops, let me go back. I didn't mean to click that. With all of them pointing in the same direction. Then oxygen. Okay, so now this is where we're going to be. Okay, so it's kind of back to the story I told you a minute ago about how when you have them all going in the up direction, then you're going to have them going down, right? So in this particular case, with nitrogen, we filled all of the available spaces, the available orbitals, okay, sublevels. So now if we add any more electrons, we're going to have to start doubling them up because we don't have any more room. So in this case, we're going to say 1, 2, 3, and then 4, the last one I draw is going to be down in the first box, and that represents 2p4. Now go over to fluorine. Fluorine is at 2p5. So now we're going to add another down arrow at 2p5. And then last you have neon, which is 2p6. So that one is going to be going down as well, okay? Now, in order to describe the probable location of electrons, they are assigned 4 quantum numbers, which are called quantum numbers. Now, I'm going to stop right there because we're not really getting into quantum numbers just yet. That's going to be later in the week. So what I'm going to do is end now, but then there's going to be another video to follow, which is your arrow diagram note sheet. So I'm actually going to go over the note sheet with you here momentarily and put that video in there, okay? So that's it for the notes. Hope y'all have a good day. And then the next day you guys are going to be doing arrow diagrams, so orbital filling diagrams. So I will go over that note sheet with you, and then we will do the assignment on orbital filling diagrams, okay? So I will see you guys soon.